This is Professor Coles. Today I'm going to be talking about the Hughes model scaling procedure, or also known as the form factor approach. If you haven't watched yet the short lecture on Froude's resistance decomposition and model scaling procedure, I would do that first. That link will be up on the website as well. So basically the idea is following that lecture we divide our total drag coefficient into three components: frictional, which is the parasitic drag from the shear stress on the hull, the wave-making component, and a form drag. And then with Froude's approach, this form component, which may be the least well known, was considered to be constant for a given geometry. So this model and the full scale shared the same form drag coefficient, and it got lumped into the residuary drag along with CW. What was done was to try to improve to try to get better correlation between models and full scale. So essentially what people found is that models that were too small were significantly in error when they scaled up to full scale. And they would know this by making a series of models that were successively larger. All of them should have scaled to the same number, full scale ideally, but they were finding the larger models were better approaching full scale size. So there was an issue, still a scaling issue at bay, and the form factor was one way to try to improve that. The idea is that you scale this form drag, instead of being a constant, you scale it as a function of the frictional drag coefficient. And what is used is a linear function, K times CF. We assume there's a linear relationship. So if you studied earlier in the class, when you think about classic flow over a cylinder or a bluff body, there's certainly Reynolds dependency to the viscous pressure drag, to the form drag. And this is trying to bring that into play. So this is the assumption that that the functional dependence of the form drag is proportional K to the friction drag. It's linearly related to the friction drag. Thus, I can make a total viscous drag, which includes both form drag effects or viscous pressure drag as well as the skin friction drag. That's going to be equal to CF plus KCF, or 1 plus K times CF. And that will be what I'll call my viscous drag, which will include both those components. So now I have the total drag on the boat I can write as CV, this viscous drag, which has those two components, plus CW, which is the wave drag. Now what I'll do is I'll go back and recompute my scaling procedure. And again, I'm starting from this premise that the wave drag, CWS, is going to be equal to, on the ship, is going to be equal to that on the model, because they're towed at the same Froude number, or corresponding speed, as Froude called it in his time. So from the total drag coefficient of the ship, CTS, is going to be the viscous drag coefficient of the ship, which again includes both the frictional component as well as the viscous pressure drag, plus the wave making on the ship. But that wave making on the ship is the same as it is on the model, and we're going to get at that by doing model testing. So this is going to be equal to CVS, the viscous drag on the ship, which we can estimate, plus the difference between the total drag on the model and the viscous drag on the model. The difference between those two is the wave drag on the model, and the wave drag coefficient on the model is assumed to be the same as the wave drag coefficient on the full scale, so these two things are the same. Now we'll write it in terms of CF, our frictional drag coefficient. So this is going to be equal to 1 plus K times CVS, times CF plus CTM minus, running out of room, 1 plus K times CFM. And let's rearrange that. So that's one form of it. It's analogous to what we had with the Froude. Rearrange it as CTS is the total drag is equal to the total drag coefficient on the model, which we can measure through a resistance test, minus 1 plus K, and I'm just going to group terms here, times the difference between the frictional drag on the model and the frictional drag on the full-scale ship. Now note the form of this is very much like the form from Froude's resistance decomposition method, except that I have this additional term here. So if k is 0, this is equivalent to the Froude form. If k is non-zero, and in general will be greater than 0, or will be greater than 0, then we bring in a new factor which causes this to deviate from Froude's approach. Now k is known as the form factor. That's the name of this thing. Form factor is a positive number. This is a small number, it's less than 1. And again, that k comes from scaling the form drag from this relationship, that the form drag is proportional to the frictional drag coefficient, linearly related to the frictional drag coefficient, where the coefficient of friction is k. We'll talk about how to calculate k in a second, but let's go back as we did with Froude and look at this diagrammatically and see what's going on. So I have Reynolds here. I have my friction coefficients here, CF, CW, CV, CF. Now I have a traditional frictional drag law that we've been working with, like your 1/5 power law, and later we'll look at the ITTC 1957 law. I have a traditional drag law, CF. Now if I multiply that by 1 plus k, I get my CV. So again, CF is equal to, somewhere here, CV equals 1 plus k times CF. So I'm multiplying this by 1 plus k, and I get another curve. We'll make it a green curve. Something like this. So that's multiplied by 1k. It's not the same as a constant addition as it essentially was with the Froude case. It's a multiplicative factor. So if I test my model, and let's say I get a total resistance coefficient right here, this blue smudge right here. The difference between that and the green line is going to be the wave drag. So here's your wave drag on the model. CWM. And this little bit right here between the green and red lines is the viscous pressure drag. And this bit here from the red line to the bottom is my frictional drag. So the CF should be labeled a little lower down. Put it down here. CFCV. So the total viscous drag is up to the green line, and the remainder is the wave drag. So this is at a low Reynolds number. This is a model's Reynolds number. At the full scale Reynolds number, I would be here. Same Froude number, higher Reynolds number. My friction takes me to this red line. The smaller frictional coefficient, the higher Reynolds number. Then I have up to my viscous drag. And I add on the same amount, because CWM equals CWS. I take this chunk and I add it on here, and that's supposed to be the same length, those two components, to get myself a total drag. I'll make both of the total drags purple, coefficients purple. So again, in this case, I'm assuming a form drag coefficient which is proportional to frictional drag coefficient, that constant proportionality being k. My frictional drag coefficient, I'm still going to rely on traditional friction formulas. I will introduce in class the 1957 ITTC line, which is quite similar when we compare it with the 1/5 line, but it was to address the fact that boats are a bit rougher than these flat plates. And so CF can be estimated with K in place. A CV can be estimated. And so the purple, or C total, can be measured on the model. So we can easily get at the wave drag on the model by just subtracting out our estimated total viscous drag. And the wave drag coefficient of the model is equal to the wave drag coefficient on the full-scale ship. And we just tack that on to the full-scale ship. Now when you think about this, the difference between this approach with a form factor and Froude's approach, which essentially did not include a form factor, really comes down to the K, where we're displacing this red line, not displacing, we're scaling this red line up to the green line. So the component that's added on, this wave drag, will be smaller because we're not including the form drag in that wave drag as we were in the Froude case. So when we go to tack this on, it gets tacked on to this point on the green line, but the viscous pressure drag coefficient is assumed to be smaller than the viscous pressure drag coefficient for the model, and thus the resulting total drag coefficient in the case with the form factor is in general going to be smaller. The model, or the ship drag, is going to be smaller with a form factor than it would be with the Froude case. So say that again, and I will go through a calculation. On Tuesday, we're going to take the same ship and use both procedures, Froude with no form factor, and this approach, the Hughes approach, with a form factor. We use the same frictional lines for both. The only difference is we're using a form factor K, which accounts for the viscous pressure drag, and in the case we will see that the form factor approach results in a smaller overall drag on the full-scale ship compared to the Froude. A slight difference. Now, so this brings in a new thing. How do we get at K? Okay. How do we get K? The form factor. So there's a couple of ways of doing it. One is you can recognize that here's our total drag, this lovely color, CW, the wave drag, plus the viscous drag. But this wave drag essentially goes to zero at slow speeds. Very slow speeds, at zero speed there is no drag of any kind, but at very slow speeds it's dominated by viscous drag. The wave drag is going to zero. So one of the ideas is basically to plot your drag coefficients versus a Reynolds number or speed, doesn't matter. And so you have your friction line, you have your CV line, just like we did in the previous diagram, and then you have your total drag coefficient line. It might look something like this. And so, I gotta stop using this hideous color. The total drag coefficient line. So the distance between the total drag coefficient line and the CV line is going to be the wave drag. It gets bigger and bigger. At high speeds, this dominates. This red line portion dominates compared to, say, the green line portion. And the further you go to the right, the more so that is the case. When you go to the left, the total resistance curve collapses into, theoretically, into the CV curve because CW is going to zero. The wave drag coefficient is going to zero quickly as you get to slow speeds. So CT will collapse into CV because this is gone. And therefore the idea is that if you get to a very low speed and you see you're here, you assume that CW is zero. And that allows you to calculate CV because you can calculate CF, and CV, you have this value which is you assume to be equal to CV. You know CF at that Reynolds number, and CV again is just 1 plus K times CF. So you know CF, you know CV, you can get a K. Now the problem is when you go to very slow speeds, you have the error in your dynamometer, or the error in your tow tank resistance measurement becomes large compared to the resistance, and so you have errors which you cannot, measurements which you can't trust. You have laminar flow, trying to keep it turbulent, and so you might have an extended laminar flow even with the stimulators, and so it gets difficult to do this. So what is typically done is use what's called a Prohaska chart. In this case, what's assumed is that towards lower speeds that the wave drag scales as, and this could be shown mathematically, the Froude number to the fourth power. CW goes as alpha Froude number to the fourth power. It allows us to say CT is equal to CV, CV plus CW, which we're assuming to be of the form alpha Froude number to the fourth. So this is equal to 1 plus K CF plus alpha Froude to the fourth. Divide both sides by CF. I have CT over CF is equal to 1 plus K plus alpha Froude to the fourth over CF. Now, this is an equation for a line where I have y equals, written a little bit backwards, but b plus m times x. The slope, m, is alpha. Your independent variable is this funny looking thing here, x. Your dependent variable is this ratio here, and your intercept, b, is 1 plus k. So then I take my model, I run it, I test it, and I plot it versus this independent variable, Froude number to the fourth, over CF, CT over CF. If my assumption is correct, actually, I'm assuming this form, if my assumption is correct, I should look at my data, and it'll be noisy, but essentially it should look like a line. If the wave drag is really scaling as CW to the fourth, and it is equation for line, and what I'm really trying to solve for is the intercept of that line, b, which is equal to 1 plus k. Where that line intercepts this axis here, this value right here is equal to 1 plus k. So if you can figure out what that intercept is, then you can figure out k, the form factor. And that's more typically used. There are some other relationships that we also use that I will go over in class. Basically, they're function fits. So people use Prohaska plots on a bunch of different boats, and you get a functional fit where you have k equals some function of typical hull characteristics. A block coefficient, for example, beam to length ratio. These are typical ones. And you will find that k increases as CB increases, as the boat gets more blocky, and k increases as the beam to length goes up for similar reasons. And so if you think about the block coefficient again, block coefficient really is, again, a measure of how much volume you're getting into the ends of the boat. So you're thinking how much your boat fits in a block, and as your block coefficient goes up, you can start with a low block coefficient boat, which might look, has to touch the sides, which might look something like this, the water plane. And you go to a high block coefficient boat, and it might look, something like this, where we've really pulled volume to the ends of the hull. Boy, this is poorly drawn. Let me at least get my first boat to have the right beam. Ugh. Drawing with my finger. Okay. Okay. So these boats have the same beam to length ratio. One is a higher block coefficient, being the dark blue line there. So when you push more volume, particularly aft, if we focus in on the aft section here, then the one that has a volume aft has a larger adverse pressure gradient. It's going to be more prone to separation. It's going to look more like a cylinder or a bluff body instead of a streamlined body. So as that block coefficient goes up, the form factor is going to go up. The beam to length ratio, we can think of the same thing. Even if they have the same block coefficient, the boat with a higher beam to length ratio is just fatter. There's an extreme boat, and we'll draw on its mirror image a boat with a low beam to length ratio. Same length boat, much narrow beam. And so that upper boat, the blue boat, will have larger scale separation in the stern compared to the green boat, which might only have some kind of minor separation. So again, as the beam to length ratio goes up, K will go up. And so there's different sort of forms for that, and there are formula given in the propulsion book, the ship hydrodynamics and ship resistance and propulsion book, which you can use. So that covers getting at K, and once you have K, you can fulfill the estimation of the full-scale drag, because you have the frictional drag coefficients that you can estimate. Going back to our final approach, which is up here. To get the total drag coefficient of the ship, first we measure the resistance of the model converted to a total drag coefficient. Somehow calculate K, which we just discussed. The frictional drag on the model can be estimated from a resistance curve, and I'll present a resistance curve in class. And for the Reynolds number of the model, you take the Reynolds number of the full-scale ship, use the resistance curve to calculate the frictional drag coefficient of the full-scale ship, and you have everything you need on the right-hand side in order to compute the total drag coefficient of the ship, and from that you can compute the resistance of the ship in newtons, the bare hull upright resistance. So that summarizes what we call the form drag approach. So again, it's a little bit more realistic in terms of how it treats the viscous pressure drag. However, it brings in a new coefficient K, and that K is connected to the geometry of the boat. And it can vary. We'll see numbers maybe as high as 0.2, but typically in the range of 0.05 to 0.15, depending upon, again, how bluff the boat is, the nature of the boat.